Hello again, this is Jerry Pinter. Welcome to part 2 of Chapter 7's lecture. In this part, we will talk about torque. So what is torque? Well, torque is the effect of a force that produces a twist or a rotation. So let's look at an example here. Suppose you want to loosen a tight bolt, which is shown right here. So you go to the toolbox and you grab this nice crescent wrench here. The question is, where should you apply the force to get the most leverage? In other words, if the bolt is really tight, where would you want to grab this wrench? Would you want to grab it close to the bolt here or far away on the handle here? Well, I think, if you've ever used a wrench, you probably realize that you want to grab and apply the force as far away from the bolt as possible to get the most leverage here. Then the other question is, what angle should you apply the force? In other words, should you push straight onto the wrench like this, or should you push along one of the ends or at an angle, or etc.? Well, again, by trial and error, you'll find out that you can produce the best effect or the most torque or twisting of this bolt here by pressing with your force at right angles to the wrench here. So this is the definition of torque here, at least for this simple example. Torque is defined as the product of the radius, meaning how far away from the axis of rotation do we actually apply the force. That's R. And then, of course, the force itself. So we multiply the radius times the force. The symbol for torque is the Greek letter tau, which is a Greek lowercase t. So we'll be using that for torque. So just to summarize here, to produce a large torque, we want a large radius, we want a large force, and we want the force to be at right angles with the radius of rotation. Let's continue looking at torque a little bit further here. We know that force causes acceleration from F equals ma, Newton's second law. But what we're talking about there is force causing a linear acceleration, meaning when we push on an object, it moves in a straight line in the direction that we push it. But the question here is, what causes angular acceleration? In other words, what causes something to speed up as it rotates? And the answer here is torque. And this is the main idea of this section of the lecture. So another demo that we could do here is, if we had a bike wheel, for example, we turn our bicycle upside down so the wheel can turn. We could experiment again by trial and error and find what is the best way to turn this wheel and get it to go fast. There are a couple things, obviously, that we wouldn't do. For example, we wouldn't want to apply the force right here at the axle. That will do nothing. Also, we wouldn't want to apply the force in this direction, in a radial direction, pointing towards the center, because that won't turn the wheel at all. So there are a couple options that are sort of good. In other words, we can push somewhere in here, let's say on one of the spokes in this direction, or maybe we could push out here at an angle, and those will certainly work to turn the wheel, but they're not the best. The best way to get the wheel to accelerate is to push out here on the rim or the edge of the wheel and to push at a right angle to the radius at which we push. So this is just like we talked about with the wrench. We want to be as far away from the axis of rotation as possible, and we also want to push at a right angle. So torque here is a perpendicular force applied to a body at a distance r from the pivot point being the axis of rotation here. And torque causes angular acceleration. So this is the cause and the effect. This is the dynamics of rotation. A torque is the cause and the effect is angular acceleration. So again, we can write torque, tau, is equal to the product of r times, now this is the force again, but this little symbol here means the force that's perpendicular or at right angles to the radius here. So kind of putting this all together, torque is the product of the distance of the force from the pivot, r, times the component of the force perpendicular to the radial line. So if we were to push on this wrench, for example, at an angle here, that's not 90 degrees. Let's say we push at it at 30 or 45 degrees, something like that. Notice we're using phi, the Greek letter phi here for the angle. Then what we want to find is this force can be broken up into two components. There is a radial component that goes along the radius here. It's parallel to the radius, but this component doesn't produce any torque at all because it's directed along the arm of the wrench here. It's this component, the perpendicular component, that does all the torque. This is the part of the force that produces the torque. So that's why we say it's the product of R times the perpendicular component of the force. And by doing a little trig here, you'll notice that this is a right triangle here, as is this one here, with this angle phi. So this component here, this perpendicular component, is given by the force, which is the force is the hypotenuse of this right triangle. And we want this leg of the triangle here, so we're going to use the hypotenuse F times the sine of phi. So this is really our full-fledged definition of torque. It's R times F times the sine of the angle between the force and the radial line. There is another method to calculate torque that is equivalent, and sometimes it's more practical or convenient depending on how the problem is set up. It involves something called the moment arm. And the way this is done is basically, if we look at our wrench situation here, or with the force at an angle here, what we do is we draw an imaginary line along the force. This is called the line of action. So this dotted line here traces out in the same direction as the force. And then what we do is measure from the pivot here, the axis of rotation, we measure the perpendicular distance to this line. So notice this R perpendicular here makes a right angle to the line of action. The other way to think of this pivot, this distance here, R perpendicular, is the shortest distance between the pivot and the line of action, and that will automatically make this right angle here. So there are two ways of stating the torque. We can say it's either equal to R perpendicular times the force, or the radius times the perpendicular component of force. But either way, we get the same geometry with this right triangle, whether we use this right triangle here, angle phi, or this right triangle here, it has the same angle phi. We always end up with RF sine phi. So we'll see that sometimes when an object is, for example, leaning relative to the ground, it's more practical to use this moment arm technique. We'll see a problem later in this section where we use the moment arm. Let's look at some more examples of torque. This one here involves a wheelchair with wheelchair basketball. And the idea here is that we want this wheelchair to be as responsive as possible. We want large accelerations of the wheelchair. Therefore, we want to maximize the torque that's applied by the athlete or the person sitting in the wheelchair. So the two things that are done here in wheelchair design are the hand rims are far from the pivot or the axle. So notice, here's the axle of rotation, and notice where the hand rim is out here. It's right at the outer edge of the wheel. So this is maximizing the radius here, R. We want that to be as large as possible. The other thing is that the athlete using the wheelchair is going to push at a right angle to this radius. So notice her arm is pushing at a right angle to the radius. This again will maximize the amount of torque, because remember, the sine of 90 degrees is 1, and that's the largest the sine can ever be. The sine is always 1 or less than 1, and the way to maximize the sine of phi is to set phi equal to 90 degrees as shown in this picture. Here's another example of torque where we're actually do some calculations here with numbers. So this is our wrench problem again. It says to loosen a bolt, you grab a wrench 25 centimeters from the bolt and pull with the 200 newtons of force at a 40-degree angle as shown. What torque do you produce? All right, so here's our picture. Here's the bolt we're trying to loosen. We've got the wrench. We've grabbed the wrench at a distance here of 25 centimeters from the bolt. Notice the force is along the arm of the person using the wrench here, and that force is aligned here at a 40-degree angle with the radius here. So remember that before we do the math here, what we're really going to be calculating is this perpendicular force here, and that's accomplished by taking RF times the sine of 40. So our equation to calculate torque, remember, is RF sine phi. So our angle is 40 degrees. Our force here is the 200 newtons. That's how much we're actually pulling with. And then the radius is 25 centimeters, which we convert to meters, so it's 0.25 meters. So we multiply these three numbers together in a calculator, and we'll get a torque of 32 Newton meters. So notice the units of torque. We get newtons from the force, and we get meters from the radius here. The sign has no units. It's just a number. Now, here's a conceptual quiz for you to think about. Suppose the bolt does not loosen. What three things could you do to increase the torque? So think about this. What would be three things you could do here to improve your torque? Go ahead and pause the video and think about those, and then we'll discuss it. Okay, so I flipped to the slide here, but the three things to increase the torque on the other slide was, one, you could obviously increase the force. You could pull harder. Another one would be to grab the wrench farther from the bolt. In other words, increase the radius R. And then the third thing you could do would be to increase the angle to 90 degrees because that maximizes the torque. Okay, so for torque, it can be positive or negative. And the way we define this is that a positive torque causes rotation in the positive direction. And remember, the positive direction of rotation is in the counterclockwise direction. In other words, this direction is positive. And the reason for that, again, is that when we rotate something counterclockwise, we are causing theta, the angle here, is increasing. So theta is becoming more and more larger, which is in the positive direction. Likewise, we can produce a negative torque if we were to push the wrench this way, in this direction. The wrench is going to rotate in the clockwise direction, and that would be a negative torque because the angle is getting smaller. Torque is sort of analogous to the concept of force. So when we talk about net force, we're talking about adding up all the forces and making sure we keep track of their directions and so forth. The same thing applies with torques. We're going to be concerned with the net amount of torque on an object because that's what's actually going to be used to calculate how much the object rotates and what the angular acceleration of the object is. So just as a sort of a conceptual example here, consider this portion. This is part of your bicycle. This is the front chain ring or front sprocket that the chain wraps around on. And these two objects here, these are the crank arms, basically where one pedal would go here and the other pedal of the bike would go here. So imagine, you're riding this bike and you have both feet on the pedals and you're pumping away there on the bike. Well, what's happening here is we're creating multiple torques here because there's a force from one foot pushing down really hard on this pedal. Your other foot might just be lightly resting on this pedal, but there might still be some force pointing down. So, you can see that both of your feet are creating torques. This torque, we would define this as a negative acting torque because it's tending to make this thing rotate in a clockwise fashion there. Furthermore, the chain is, tight and it's pulling on this chain ring. So the chain is exerting a torque as well on this system here. And we would, measure the radius from the axle here, the pivot, up to where the force is applied. And this force here, that would be a positive torque, right? Because that's trying to cause this thing to rotate in the counterclockwise direction, which is the positive direction. So the idea here is that, we could, by doing some math, we could just add up the effect of all these torques and add them all together. So the net torque for a system is just summing up all of the torques and calculating each of them and adding them together as needed. Let's do an example here where we're going to calculate the acceleration of a lightweight beam balance. That we're kind of jumping ahead a little bit. In this part of the problem, what we're only going to do is figure out what the net torque is and figure out which way it rotates or accelerates. We will figure out the actual acceleration in a later part of this video. But for now, let's see what we've got here. We've got a 6-meter long, thin, lightweight pole, and it's set on this balance here, this triangular, is called a fulcrum. 2 meters from this end here, and of course the whole thing is 6 meters long as shown, and there's 2 masses placed on the ends of this balance. There's a 20 kilogram mass here and a 60 kilogram mass here. And we're going to assume in this problem that this pole is like a very lightweight hollow tube that is negligible mass compared to these heavy masses here. So we're going to ignore the mass of the pole itself. So the question is, what is the net torque, and which way does the system rotate? In other words, does this thing rotate, does this weight over here fall, or does this weight over here fall? And so there's a rotation this direction counterclockwise, or will it be clockwise? So let's go ahead and do this problem. So the solution is first to draw and label the 2 forces that produce torque about the pivot point. So the pivot point here of this problem is where the beam is balanced, right here on the fulcrum here. And the 2 forces that are involved are the weights of these 2 masses. So remember, to calculate weight, it's just mg. So we'll call this mass 1, so that's m1g. And then this object has a weight of m2g. And of course, weight, as always, points down. So these weights are forces that are going to create a torque that's going to cause this balance beam here to rotate one way or the other, depending on which torque dominates. So let's go ahead and do the math here. So to find the net torque, we're going to add up the torques of these 2 forces here. So let's start with this one, because this is creating a counterclockwise rotation in this direction, right? If this were the only mass on the balance beam, this thing would obviously rotate downward. And so this is a positive torque over here, all right? Remember, we defined positive torque as one that causes a counterclockwise rotation. So I have the radius is 4 meters, all right? Now I got that because I know the whole thing was 6, and we were told this was 2, so this must be 4 meters. And then we multiply the radius times the force, and the force is m1g, okay? And m1 is, let's see, here it is, 20 kilograms, and then g, of course, is 9.8. Now, the second torque is caused by this mass over here. Now, this one is tending to rotate this system in a clockwise direction, in this direction. So that is a negative torque. So we're going to subtract 2 meters, right, is our radius, times this force, which is m2g, and m2 is 60. Okay, so when you do the math here, when you figure out this term and then subtract this term, well, this term here is bigger, and so we're going to end up with a negative torque, negative 392 Newton meters. I forgot to put the units in there. Okay, but that is our net torque. So since the torque is negative, this beam here will rotate clockwise. Okay, so it's actually this mass here is going to fall down, and this light mass over here is going to rise up. For our last example of this part of the lecture, let's look at a sports science example. This is calculating the torques involved with lifting weights, and in this particular one, we're going to analyze a simple weightlifting movement called a curl, which you can use to strengthen your biceps muscles in your arms. So the way this exercise is done, it can be done using either a barbell, with both hands on the bar, or in this case, the woman is doing a one-arm curl with a dumbbell. And what you're doing here is, she's going to raise this weight up and down like this, keeping her upper arm still. She's just going to move the weight kind of in an arc like this. So what's happening here, from a physiological standpoint, is that inside the arm, the lifting muscle is the biceps muscle here, and muscles always work by contracting. When you flex a muscle, the muscle actually contracts and it pulls. So muscles create tension. So you can see how this works here. There's the elbow joint down here, and the bicep muscle has an insertion point where the tendon, which attaches to the muscle, hooks onto the bone right here. Notice it's not right at the elbow. It's a little bit displaced from the elbow by a distance of 4 centimeters here. So when this muscle contracts, when it pulls, it's going to tend to create a torque and cause the lower arm to rise up. And by lifting with enough force, you'll be able to lift this weight here. So we can sort of model this system here, the arm, by a simple model here. We've got 2 rods. These represent the bones in the arm. This is the upper arm here. Notice there's a hinge right here. That's that's the elbow joint. And then these are the bones in the forearms, are modeled just by a simple lightweight rod here. So the force here is basically, there are 2 forces at play here. There is the muscle force, the tension force of the bicep is pulling right here. Remember, it's 4 centimeters from the pivot. And then out here on the end of our arm, of course, is the weight. All right, and we're told that this dumbbell weighs 20 pounds, which is 89 newtons. So this force here is an 89 Newton downward force, okay? So what we're going to do here, and we're also told in this problem that the biceps tendon is pulling upward with 900 newtons of tension. Okay, so we know what this force is here. It's 900 newtons. So the net torque here, remember what we do is we add the torques together. So we've got this force here is causing the arm to rotate in a counterclockwise direction like this, okay? This weight out here, the dumbbell, wants to make the arm fall down, and that is a rotation around the elbow in a clockwise direction. So this is a positive torque again, and this would create a negative torque. So when we add our torques, we'll do the positive one first. So the rate, remember, torque is radius times force. So the radius was 4 centimeters, which is 0.04 meters, times the tension in the muscle, which was given as 900 newtons. And then we subtract, because this is a negative torque, 0.35 meters. We were given that this distance here is 35 centimeters from her elbow to her hand. So that's 0.35 meters. And then remember the weight here, the 20-pound weight, I converted that to newtons. It has a weight of 89 newtons. That's the downward force. So this upward torque is 36 Newton meters. The downward torque was 31 Newton meters. So when we subtract them, we end up with a net torque of 5 Newton meters. Now, this is a positive torque. So that means this weight and her arm are going to rotate in a positive direction, which, remember, is counterclockwise. So in other words, she will, by applying this much force, she will be able to lift this weight and it'll rotate upward. All right. By the way, it's interesting to see here from a physiology standpoint of what's required to basically lift a light weight. Like, 20 pounds is not that heavy. Any of you could do that quite easily. But in order to lift that, you have to generate a lot more tension than 20 pounds in this muscle and in the tendon because of the leverage involved here. So the 900 newtons of tension equates to about 200 pounds. And that's just one arm. So this bicep muscle here is pulling with a force of about 200 pounds. That's the tension in that tendon. Just to lift a weight, that's roughly 10 times lighter than that. And the reason for this, again, is leverage. You can see that this is a very small distance here compared to this large distance here. So it's required to have a much larger tension in the muscle than what you're actually lifting. And that also brings into play some interesting strength advantages. Some people are, I guess, lucky. They're born with this distance here, this insertion point. If it's shifted down a little bit farther in the arm, they'll have considerably more leverage in lifting. And so that gives some people a natural strength advantage. And some animals, for example, I've heard that bears, their tendon insertion point is way down the arm here, giving them, superhuman strength basically compared to us humans. Okay, guys, so that is it for this part of the lecture. We'll continue on next with part 3.